Somewhere inside a star, or in the invisible bubble of magnetism wrapped around our own planet, energy is quietly stockpiling. For hours, sometimes longer, a magnetic structure winds tighter and tighter, hoarding power the way a drawn bow hoards force, silent, patient, invisible. And then, in the span of a few minutes, it lets go. Not slowly, not gently. A reservoir of energy built up across a region larger than entire worlds is unleashed almost at once, flinging charged particles toward the speed of light and heating matter to tens of millions of degrees. It looks, for all the world, as though the magnetic field has suddenly torn itself open. But magnetic fields are not ropes, and nothing physically snaps. So what actually breaks in those final, violent minutes? Tonight, we follow this energy from its silent build-up to its explosive release, and uncover the hidden switch that flips. Before we go further, if you find this kind of deep dive into how the universe actually works fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Picture something building in complete silence. Not a sound, not a flicker, nothing you could point to and say, there, that is where the danger lives. Just a region of hot, electrically charged gas, somewhere in the atmosphere of a star, or in the invisible magnetic cocoon wrapped around a planet, slowly winding itself tighter. Over minutes, then hours, sometimes far longer than that, energy accumulates inside the magnetic structure threading through that gas. It builds the way tension builds in a drawn bow, or in a spring compressed a little more with every passing moment. Nothing looks violent, nothing looks unstable. And then, without any obvious warning, in the span of just a few minutes, all of it lets go at once. This is the central mystery we are chasing tonight. A magnetic structure can hoard energy quietly for hours, spread across a volume larger than entire worlds, and then release a staggering fraction of that energy almost instantly. Charged particles get flung outward at speeds approaching the speed of light. Matter gets heated to tens of millions of degrees, far hotter than the surface of the star that produced it. Radiation floods outward across the spectrum, and to anyone watching, it genuinely looks as though the magnetic field has suddenly ripped itself open, as though something that was holding tight simply tore apart. But here is the first thing you need to understand, and it will shape everything that follows. Magnetic fields are not ropes. They are not threads. They are not physical strings that can be pulled taut and snapped. Nothing material breaks in those violent final minutes. And yet, something absolutely does change. Something profound. Something that flips like a switch and converts a slow, patient build-up into a sudden, explosive release. To understand what tears open, we first have to understand what was holding together in the first place. And to understand that, we have to start with the strange, restless substance where all of this unfolds. That substance is plasma. You have almost certainly heard the word, and you may have heard it called the fourth state of matter, alongside solid, liquid, and gas. That description is fine as far as it goes, but it hides the thing that actually matters for our story. In an ordinary gas, the atoms are neutral. Each atom has its electrons bound closely to its nucleus, and the positive charge of the nucleus is balanced by the negative charge of those electrons. So from the outside, every atom looks electrically neutral. Push on a neutral gas with a magnet and almost nothing happens. The gas simply does not care. Plasma is different because the electrons have been torn loose. Heat a gas hot enough or bombard it with enough energy, and the electrons get ripped away from their nuclei. What you are left with is a churning sea of free negative charges, the liberated electrons, mixed together with the positively charged ions they left behind. Nothing is neutral anymore at the level that counts. You now have a substance made of enormous numbers of independent charged particles, all free to move, all free to respond. And that single fact changes everything about how the material behaves. There is one more thing this liberation of charges buys you, and it turns out to be the quiet foundation of the entire story. A gas of neutral atoms is an electrical insulator. Push a voltage across it and essentially nothing flows, because there are no free charges to carry a current. But the moment you tear the electrons loose and turn that gas into a plasma, you have created a sea of mobile charges. And a sea of mobile charges is an extraordinarily good electrical conductor. In fact, a sufficiently hot, well-ionized plasma can conduct electricity so freely that in the ways that matter for our story, it rivals or even outdoes the copper in your household wiring. And this near-perfect conductivity is not a side detail. It is precisely the property that will, a little later, weld the plasma and the magnetic field into a single, inseparable unit. The better a material conducts, the more fiercely it resists any change to the magnetic field threading through it, because any such change instantly drives currents that fight back. Hold that idea lightly for now. A plasma is a superb conductor, because it is the hidden reason the field and the plasma will prove so maddeningly hard to pull apart, and therefore the hidden reason the energy can pile up for so long before it finally breaks free. Because here is a rule that sits at the very foundation of physics. Charged particles feel electric and magnetic fields, and neutral particles largely do not. An electric field pushes on a charge directly, shoving positive charges one way and negative charges the other. A magnetic field is subtler. It does not push a charge that is sitting still, but the moment a charge moves, the magnetic field bends its path, curving it, forcing it to spiral. So in a plasma, where practically every particle is charged and practically every particle is in motion, electric and magnetic fields are not gentle background influences. They are the dominant force in the room. They dictate how the particles move, where they go, and how they organize themselves. This is why we say plasma responds strongly to fields. It is not an exaggeration. The fields and the particles are locked in a constant, intimate conversation, each one shaping the other. Now follow that conversation one step further, because this is where it gets beautiful. We just said that moving charges get bent by magnetic fields, but moving charges do something else, something you already half know from the wires in your walls. A stream of moving electric charge is, by definition, an electric current. That is all a current is, charge in motion. In a copper wire, the moving charges are electrons drifting through metal. In a plasma, the moving charges are those free electrons and ions, and they are everywhere, in unimaginable numbers, streaming and swirling through the whole volume. So a plasma is not just a substance that feels currents from the outside. A plasma is threaded through with its own internal electric currents, generated by its own charges as they move. And this is the hinge the entire story swings on, because electric currents produce magnetic fields. A current flowing through a wire wraps a magnetic field around itself. That is how an electromagnet works, how the motor in your refrigerator works, how essentially every piece of electrical machinery you own works. The same law holds in plasma. The currents flowing through the charged gas generate magnetic fields, and those magnetic fields in turn steer the charges, which changes the currents, which changes the fields. Round and round it goes. The plasma and the magnetic field are not two separate things that happen to share the same space. They are two aspects of one coupled system, each continuously creating and being shaped by the other. So we have charges that feel fields, motion that makes currents, and currents that make fields. Hold on to that loop, because it is the machinery underneath everything. But there is still one ingredient we have not addressed, and without it, nothing about a sudden violent release would make any sense at all. Where is the energy? What exactly is it that builds up quietly for hours and then bursts free? To answer that, we need to accept something that is not intuitive at first. A magnetic field, all by itself, holds real, physical, meaningful energy. We are used to thinking of energy as belonging to objects. A moving car has energy because it is moving. A stretched rubber band has energy because it is stretched. A hot cup of coffee has energy because its molecules are jostling. In each case, we can point to matter and say, the energy is in there, in that stuff. So it feels strange to be told that empty space with a magnetic field running through it contains energy, even if there is nothing obviously moving. But it does. A magnetic field is not a mere abstraction or a way of drawing arrows on a diagram. It is a physical condition of space, and setting up that condition costs energy, and that energy stays stored in the field until something releases it. Think about how much effort it takes to force two magnets together the wrong way, North Pole shoved against North Pole. You can feel the resistance in your hands, the invisible pressure pushing back. The work your muscles do fighting that resistance does not vanish. It goes into the magnetic arrangement itself. The more intensely you configure a magnetic field, the more strongly it is bunched and bent and compressed, the more energy is packed into it. And in a plasma, where the currents are enormous and the fields they generate can be twisted into fantastically complicated shapes, the amount of energy that can be stored this way is genuinely vast. This is the reservoir. This is what fills quietly. When we say energy accumulates inside a magnetic structure for hours, we mean that literally. The field is being pushed into a more and more energetic configuration, and it is holding that energy the way a compressed spring holds it, waiting. Now, to talk about that structure, we need a way to picture it, and here we have to be extremely careful, because the picture we use is also the picture most likely to mislead you. To visualize a magnetic field, physicists draw what are called field lines. You have seen them. Sprinkle iron filings around a bar magnet, and they arrange themselves into graceful curving arcs, sweeping from one pole to the other. Those arcs trace the direction of the magnetic field at each point in space. Where the lines crowd close together, the field is strong. Where they spread apart, the field is weak. They are an elegant, powerful, genuinely useful way to make an invisible thing visible. But field lines are a description, not a substance. They are a bookkeeping device, a visual and mathematical tool for keeping track of two things: which way the field points, and how different regions of the field are connected to one another. There is no actual thread strung through space. If you flew a spacecraft into a magnetic field, you would not find physical filaments you could snag or cut. The lines are imaginary reference marks laid over a smooth, continuous field, exactly the way the lines of latitude and longitude are imaginary marks laid over a smooth, continuous planet. The equator is a real and useful idea, but you cannot trip over it, you cannot pick it up, and you certainly cannot snap it in two. I am belaboring this point on purpose, because almost every casual description of what we are building toward gets it wrong in exactly the same way. You will hear that magnetic field lines break and reconnect, and you will picture two ropes fraying and being retied. That image is the single most common misunderstanding of this entire subject, and it will actively prevent you from understanding what really happens. So plant a flag here, right now. Field lines are how we track the field's direction and connectivity. They are not objects. When we later say connectivity changes, we will mean something precise and physical, and it will have nothing to do with material threads snapping. Keep that firmly in mind, and the rest will come into focus. With the field lines understood as a map rather than a thing, we can finally describe the relationship that dominates almost all of the plasma in the universe. The relationship that makes the eventual release so dramatic precisely because it is so hard to break. In most plasmas, most of the time, the charged gas and the magnetic field are effectively glued together. Wherever the plasma goes, the field goes with it. Wherever the field bends, the plasma bends with it. They move as a single unit, an inseparable partnership. Physicists have a wonderfully vivid name for this condition. They call it the frozen-in state, as though the magnetic field were frozen into the plasma, like a design frozen into a block of ice. Let me make sure the frozen-in idea lands, because it is the load-bearing concept for everything to come. Imagine a clear block of ice with a coloured thread frozen deep inside it. Now slide the block across a table. The thread slides too, at exactly the same speed, in exactly the same direction, because it is trapped in the ice. Bend the block, if you could, and the thread bends with it. Twist the block, and the thread twists. The thread cannot move independently of the ice, and the ice cannot flow past the thread. They are stuck to each other. In the frozen-in state of a plasma, the magnetic field lines play the role of that thread, and the plasma plays the role of the ice. If a parcel of plasma drifts to the left, it drags its portion of the magnetic field to the left with it. If the field is forced to shift, it hauls the plasma along. Neither can slip freely past the other, They are welded together by the physics of charged particles and fields. Why does this welding happen? It traces right back to the loop we built earlier. Remember that magnetic fields only bend charges that are moving, and remember that any attempt to make the field and the plasma slide past each other would require charges to cross field lines. But the instant a charge tries to cross a field line, the magnetic field bends its path and forces it to curl right back, resisting the crossing. On top of that, if the field ever started to slip relative to the plasma, that relative motion would immediately drive powerful electric currents, and those currents would generate magnetic fields that oppose the slipping. The system fights any attempt to separate the two. The plasma and the field enforce their own partnership. Left to itself, with nothing exotic going on, a plasma keeps its magnetic field locked in place with remarkable fidelity, and the field keeps its grip on the plasma just as tightly. This frozen-in behaviour is not a rare special case. It is the ordinary, everyday state of the overwhelming majority of plasma in the cosmos. The gas billowing through the outer atmosphere of a star obeys it. The vast clouds of ionized material drifting between the stars obey it. The plasma streaming outward from our own star and washing over the planets obeys it. In all these places, to an extraordinarily good approximation, plasma and magnetic field travel as one. Scientists capture this whole picture in a framework called ideal magnetohydrodynamics, a long name that simply means the study of how magnetized, electrically conducting fluids move when the frozen-in condition holds perfectly. And that word, ideal, is doing quiet but important work. It signals an approximation, a description that is astonishingly accurate almost everywhere, but that quietly assumes the plasma and the field can never come unstuck. Tuck that word away. We will come back for it, because the entire violent phenomenon we are chasing lives in the narrow place where that ideal assumption stops being true. Now let us put these pieces together and watch the paradox start to sharpen, because the frozen-in state is exactly what makes the quiet build-up possible. If the field and the plasma are locked together, then whenever the plasma moves, the field is forced to move with it, and plasma is almost never still. In the atmosphere of a star, it churns and boils, driven by heat rising from below, the way water roils in a pot. Great convective currents haul plasma up, spread it out, and drag it back down. Different regions flow in different directions and at different speeds, and because the magnetic field is frozen into all of that restless motion, the field gets dragged along too, stretched here, compressed there, sheared and wound wherever the plasma flows carry it. Think again about that coloured thread frozen in ice, but now imagine the ice is not a solid block, but something more like slowly churning taffy, folding over on itself, some parts pulled one way and some the other. The thread, trapped inside, gets stretched and looped and tangled by all that folding. It has no choice. It goes where the material takes it. In just the same way, the constant, ceaseless motion of plasma in a star's atmosphere takes hold of the magnetic field and works it into ever more strained, ever more contorted configurations. And every time the field is stretched or twisted or compressed against its will, work is being done on it. Energy is being poured in, the reservoir is filling. This is the quiet build-up, and now you can see why it is quiet. Nothing dramatic is happening moment to moment. Plasma is just doing what plasma does, flowing and churning as it always has. The magnetic field is just being carried along as the frozen-in condition demands. But drop by drop, the churning motion is loading the field with energy, packing it into more and more strained arrangements, the way slow, steady cranking loads a catapult or winds a spring tighter and tighter. Hours can pass this way. The field grows more stressed, more energetic, storing an ever larger reservoir across an ever larger volume, and from the outside, it all looks perfectly calm. That calm is deceptive. It is the calm of a bow being drawn, of tension building with nowhere yet to go. And that brings us right up to the edge of the mystery, the question that the rest of our journey exists to answer. If the plasma and the magnetic field are so thoroughly locked together, if the frozen-in condition holds with such stubborn fidelity across almost the entire cosmos, then how does the energy ever get out? A drawn bow only does something useful when the string is released. A wound spring only unleashes its stored energy when the catch is tripped. As long as the field and the plasma stay perfectly welded, the energy simply keeps accumulating, held in place by the very partnership that stored it. The frozen-in state is a superb jailer. It locks the energy away, and it locks it away well. So what could possibly break that lock? What is the catch that trips? What flips the switch from patient hoarding to explosive release, and does it in mere minutes after hours of stillness? Here is the first tantalizing hint, and we will spend the rest of our time unfolding it. The frozen-in condition is an approximation. It is the ideal, the near-perfect rule that holds almost everywhere. But almost is not the same as always. There are special places, tiny places, where the plasma cannot quite keep its grip on the field, where the welding fails, and the two are briefly allowed to slip past each other. These places do not form on their own out of nowhere. The very same churning motion that stores the energy also, if the geometry is right, drives the field into a configuration that manufactures such a place, squeezing regions of oppositely pointing field together into a razor-thin layer where the ordinary rules can no longer hold. And when the lock fails inside that thin layer, even for a moment, the field is suddenly free to rearrange itself into a lower energy configuration. All that stored energy, built up across a region vast beyond easy imagining, finds a doorway, and it pours through that doorway all at once. That is the shape of the answer, but it is only the shape. We have not yet seen how oppositely directed fields get pressed together, or why they thin into a sheet, or why the ideal description that works so beautifully everywhere else specifically collapses in that one small region. We have not seen what actually decouples the plasma from the field, or how the field's connectivity genuinely changes without any thread ever snapping, or how the reshuffled field then flings plasma outward at tremendous speed and dumps its hoarded energy into heat and light and racing particles. Each of those is a piece we still have to place. But look at what we already hold. We know that plasma is a sea of free charges, and that free charges are the reason plasma bends so completely to the will of electric and magnetic fields. We know that those charges, always in motion, are living electric currents, and that currents give birth to magnetic fields, closing a loop in which field and plasma endlessly shape one another. We know that a magnetic field is not a bookkeeping trick, but a genuine storehouse of energy, and that the more strained its configuration, the more energy it holds. We know that field lines are a map of direction and connectivity, never a substance, never a thread, a distinction that will keep us honest all the way to the end. And we know that, almost everywhere, plasma and field are frozen together into a single unit, so faithfully that the restless motion of the plasma steadily works the field into more and more energetic shapes, without ever letting the stored energy escape. We have, in other words, assembled the loaded bow. We have watched it draw back silently over hours, storing more force with every moment. What remains is to find the fingers that release the string. The small, strange, localized place where the frozen grip fails, where oppositely pointing fields meet in a knife-thin layer, and where, in a handful of minutes, a magnetic structure that spent hours quietly gathering energy appears to tear itself open and hurl that energy into the surrounding world. To understand that tearing, we now have to watch the plasma do the one thing the frozen-in state seemed designed to prevent: force two opposing magnetic regions into a single thin seam and set the stage for the lock to break. We left the plasma in the middle of an act that seems almost self-defeating. The magnetic field is frozen into the churning gas, storing energy with every twist and stretch, yet that same frozen grip is precisely what keeps the energy locked away. To find the release, we have to watch the plasma do something that sounds, at first, like it should be impossible. Take the very stiffness of the frozen-in state and use it not to prevent drama, but to manufacture it. Because here is the thing that is easy to miss. The frozen-in condition is not a peacemaker. It is the reason the tension can build to such extremes in the first place. A rope that snapped the instant you pulled on it could never store the force of a taut climbing line. It is precisely because the plasma and the field refuse to slip past each other that the motion of the gas can wind the field tighter and tighter, loading it far beyond what any easily broken arrangement could hold. So let us look more carefully at what that winding actually does to the field, because the shapes the field is forced into are not random. They matter enormously for what comes next. When plasma flows, it can act on the frozen-in magnetic field in a handful of distinct ways, and each one loads energy into the field differently. The plasma can stretch the field, dragging one end of a magnetic region away from the other, so the lines running between them are pulled taut, like taffy drawn out between two hands. It can compress the field, pushing regions of magnetism closer together, so the lines crowd into a smaller space and the field there grows stronger. It can twist the field, rotating one patch of plasma relative to another, so the lines threading between them wind around each other, like the strands of a rope being spun up. And it can shear the field, sliding neighbouring layers of plasma past one another in opposite directions, so the field caught between those layers gets raked sideways and bent into a steep, straining gradient. Every one of these motions does work on the field, and every one of them stores energy in it, but they do not all store the energy the same way, and this distinction is going to become the heart of the matter. When you stretch a magnetic field, you are fighting something real, because a magnetic field under tension pulls back. This is one of the least intuitive and most important properties of magnetism, so let me slow down on it. A magnetic field line behaves, in a rough but genuinely useful sense, as though it were under tension along its length, like a stretched elastic band that wants to shorten and straighten itself. Pull a magnetic region into a long, thin, stretched configuration, and it resists, and it stores the energy of your pulling, and it holds a persistent urge to snap back toward a shorter, straighter, lower energy shape. Remember that urge. It will return at the climax of this whole story, as the force that hurls plasma outward. But for now, simply register that a stretched field is a loaded field, a spring under strain, straining to contract. Alongside that tension, a magnetic field also behaves as though it has pressure, a sideways push. Where field lines are crowded close together, where the field is compressed and strong, they press outward against their surroundings, resisting being packed any tighter, the way the molecules of a compressed gas push against the walls of a cylinder. Squeeze a magnetic region and it pushes back, and this magnetic pressure is going to matter just as much as the tension, because it governs what happens when the plasma tries to force two different magnetic regions into the same small space. Now hold both of those properties in mind, tension along the lines and pressure across them, and let us set up the specific situation that leads to a sudden release. Everything so far has been general. Plasma flows, the field gets worked into strange shapes, energy accumulates. But the dramatic, explosive kind of release does not come from just any strained configuration. It comes from a very particular geometry, one that the churning plasma is surprisingly good at producing, and once you see it, the whole mechanism starts to click into place. Imagine two neighbouring regions of plasma, each carrying its own magnetic field, and imagine that in one region, the field points in one direction, while in the adjacent region, the field points in very nearly the opposite direction. Picture, on the left, field lines running upward, and on the right, close beside them, field lines running downward. This is not a contrived or exotic arrangement, it arises naturally all the time. In the atmosphere of a star, great loops of magnetic field arch up out of the surface and back down again, and where two such loops sit side by side, or where a loop is folded over on itself, or where the shearing motion of the plasma drags one patch of field one way and its neighbour the other, you readily end up with two lanes of magnetic field pointing in opposing directions, separated by only a thin boundary. The same thing happens where the magnetised wind from a star sweeps against the magnetic bubble around a planet, and in countless other settings. Oppositely directed fields lying near one another is one of the most common situations in all of plasma physics. Now what happens if the plasma flows push these two opposing regions toward each other? This is where the frozen-in condition and the magnetic pressure start to work together in a way that sets the whole trap. Because the field is frozen into the plasma cannot simply carry its field into the neighbouring region and let the two fields overlap and blur together. The frozen-in rule forbids that kind of easy mixing. Instead, As the plasma drives the two opposing fields toward each other, they meet at a boundary and they press against each other, each pushing back with its magnetic pressure, neither able to pass through the other. It is a standoff. Two opposing magnetic regions, driven together by the motion of the plasma, jammed up against a boundary between them, each held in place by the frozen-in grip of its own plasma, each pressing on the other with the outward push of its field. And as the plasma keeps driving them together, something has to give at that boundary, but not in the way you might expect. The fields cannot merge, and neither one can retreat, so the boundary between them gets squeezed. The layer separating the upward-pointing field from the downward-pointing field grows thinner and thinner. Think of what happens on the two sides of that boundary. On one side, the field points strongly up. A tiny distance across the boundary, the field points strongly down. That means, across that narrow layer, the magnetic field reverses direction over a very short distance. And a field that changes rapidly over a short distance is exactly what physicists mean by a steep magnetic gradient. As the plasma flows press the opposing regions together and thin the boundary, the gradient across that boundary becomes more and more extreme. The field is not just strong there, it is changing violently over a razor-thin span, flipping from one direction to the very opposite almost instantly as you cross the layer. This thin, high-gradient boundary layer has a name, and it is one of the most important structures in this entire subject. It is called a current sheet. And to understand why it is called that, we return once more to the loop we built in the very beginning, the deep connection between magnetic fields and electric currents. Recall that electric currents create magnetic fields, and that wherever a magnetic field changes across space, there must be an electric current present to account for that change. It is a strict rule of electromagnetism. A magnetic field cannot reverse direction across a thin layer unless a sheet of electric current is flowing through that layer. The steeper the reversal, the thinner the layer over which the field flips, the more intense the current running through it must be. So look at what the plasma has built. By driving two opposing magnetic regions together and squeezing the boundary between them into an ever thinner layer, the plasma has concentrated an electric current into that same thin layer and concentrated it more and more intensely as the layer thins. This is the current sheet, a narrow sheet-like region, sometimes extraordinarily thin, where the magnetic field reverses direction and where a powerful, concentrated electric current flows. All the strain that the plasma has been loading into the field, all that stored magnetic energy from the opposing regions pressed together, is now hovering right at the edges of this thin, current-carrying seam. The current sheet is where everything comes to a head. It is the pinch point, the narrow throat through which the whole drama will play out. Let me make the scale of this vivid, because the geometry is genuinely striking. The magnetic regions being pressed together can be enormous, spanning distances larger than entire planets, holding energy across gigantic volumes. But the current sheet that forms between them can be staggeringly thin by comparison, a boundary layer whose thinness is measured on scales unimaginably smaller than the vast regions feeding into it. You have a colossal reservoir of stored magnetic energy distributed across a huge structure, and it is all funneling down toward a seam so thin it is almost a mathematical surface. Picture two great slabs of strained magnetism, each the size of a world, meeting along a single knife edge. That mismatch in scale, vast storage above, a hair-thin seam at the meeting point, is not an incidental detail. It is central to why the release, when it comes, is so sudden and so violent. Energy gathered slowly across an immense volume is going to find its exit through a tiny doorway, and everything that pours through that doorway does so in a rush. But now we run headlong into a problem, and it is a beautiful problem, because it is exactly the point where our reliable, trustworthy description of plasma begins to fail. Everything we have said so far, the frozen-in condition, the field driven together by plasma flows, the thinning boundary, the forming current sheet, all of it fits comfortably inside that framework we named earlier, ideal magnetohydrodynamics, the description of a perfectly magnetized fluid in which plasma and field move as one. Ideal magnetohydrodynamics is superb. It correctly predicts how the plasma flows drive the fields together. It correctly predicts the formation of the current sheet. It is one of the most successful tools in all of plasma physics, and it works across an astonishing range of situations. But it carries within it that one quiet assumption we flagged at the very start, the assumption hiding inside the word ideal. It assumes the frozen-in condition never fails. It assumes the plasma and the field can never, ever slip past each other. Not a little, not anywhere. Never. And that assumption, followed to its logical end inside a current sheet, produces something that cannot be the whole truth. Because if the frozen-in condition truly held with perfect fidelity, then, as the plasma keeps driving the opposing fields together, the current sheet would just keep thinning forever. The boundary would grow thinner and thinner without limit, the magnetic gradient across it would grow steeper and steeper without limit, and the electric current concentrated in it would grow more and more intense without limit. The plasma would keep pushing, the field could never rearrange, and the system would head toward an ever more extreme, ever more concentrated, ever thinning seam, with no way to ever release the energy piling up on either side. That is what ideal magnetohydrodynamics, taken absolutely literally, predicts. A boundary that thins toward nothing and never lets go. But that is not what nature does. Nature releases the energy. The build-up does end, and it ends explosively, in minutes, after all those hours of patient accumulation. So the ideal description, for all its power, must be missing something. It must break down somewhere. And the somewhere is exactly that thinning current sheet. The whole point of ideal magnetohydrodynamics is that it treats the plasma as a smooth, perfectly conducting fluid in which the field is flawlessly frozen. That treatment is magnificent when the structures are large and smooth and gently varying. But inside a current sheet that has thinned to an extraordinary degree, the structures are no longer large, smooth, or gently varying. They are sharp, they are concentrated, the field reverses over a tiny span, the current is jammed into a razor-thin layer. And when the scales become that small and that sharp, the smooth fluid approximation that made ideal magnetohydrodynamics work in the first place simply stops applying. This is worth pausing on, because it is the conceptual pivot of the entire subject. Ideal magnetohydrodynamics does not fail because it was wrong. It fails because it was always an approximation, valid under specific conditions, conditions of large, smooth, slowly changing structure, and the thinning current sheet drives the plasma out of those conditions and into a regime the approximation was never built to describe. It is like a smooth, gently curving map of a coastline. From a distance, the coastline looks like a clean, continuous line, and a smooth curve describes it beautifully. But zoom in far enough, and the smoothness dissolves into jagged rocks and grains of sand that no gentle curve can capture. The smooth description was never a lie. It was simply an approximation that stops matching reality once you look closely enough. In the same way, ideal magnetohydrodynamics is a smooth description of the plasma, and the current sheet is the place where you are forced to look so closely that the smoothness dissolves and the approximation gives out. And notice something crucial about where this breakdown happens. It does not happen everywhere. The vast regions of strained field feeding into the current sheet are still large and smooth, and out there, the ideal description still holds perfectly well. The plasma and field are still frozen together across all of that enormous volume. The breakdown is confined to the current sheet itself, to that hair-thin seam where the field reverses and the current concentrates. It is a localized failure. Almost the entire structure remains faithfully frozen in, obeying the ideal rules, storing its energy. Only in the tiny throat of the current sheet does the ideal description collapse. And that localization is exactly what we need to make sense of the paradox we started with. It explains how energy can be stored across a region larger than worlds, while the doorway for its release is vanishingly small. The storage is a large-scale, ideal, frozen-in affair. The release will be a small-scale event, happening in the one narrow place where frozen-in behavior can no longer hold. So we have arrived at a very specific and very interesting frontier. The plasma flows have pressed two opposing magnetic regions together. The boundary between them has thinned into a current sheet, where the field reverses sharply and an intense electric current flows. On either side of that sheet sits an immense reservoir of stored magnetic energy, strained and waiting. And right at the sheet, the trusted ideal description of the plasma has run out of road. The smooth, fluid, perfectly frozen picture that governs the rest of the structure cannot tell us what happens inside that seam. Something else must be going on there. Some physics that ideal magnetohydrodynamics leaves out. Some process that lets the plasma and the field finally, locally, slip their leash. Let me be precise about what that missing physics has to accomplish, because framing it clearly now will make the next stretch of our journey much easier to follow. For the stored energy to release, the frozen-in condition has to break inside the current sheet. That is the non-negotiable requirement. As long as the plasma and the field stay perfectly welded, the opposing fields can only ever be pressed harder together. They can never rearrange into a lower energy configuration, because rearranging would require the field to move relative to the plasma, and the frozen-in rule forbids exactly that. So whatever is going on inside the current sheet, its essential job is to loosen the weld. It has to be some process that allows the magnetic field within that thin seam, and only there, to slip a little relative to the plasma it is embedded in. Just a little, just in that tiny region, but enough. And here we can already sense why this small local slippage would be so consequential. If the field can slip relative to the plasma inside the current sheet, then the strict rule that kept the two opposing fields forever separate no longer applies right there. The upward pointing field and the downward pointing field, which the frozen-in condition had held rigidly apart, can finally interact across the seam. The magnetic connectivity across the current sheet, the pattern of which regions are magnetically linked to which, becomes free to change. And the moment the connectivity can change, the field is no longer trapped in its high-energy, oppositely pressed configuration. It can reshuffle itself into a new arrangement with less stored energy, and all the energy that was locked in the old configuration is suddenly free to go somewhere else. That is the doorway. The breakdown of the frozen-in condition inside the thin current sheet is the doorway through which the vast stored energy will pour. But I have been careful, all through this, to say only that the frozen-in condition breaks, without yet saying how. And that reticence is deliberate, because the how turns out to be genuinely subtle and genuinely varied. It is not one single mechanism. What actually loosens the weld inside a current sheet depends on the nature of the plasma itself, on how dense it is, how hot it is, how often its particles collide with one another, how turbulent it is, and how its individual electrons and ions behave when you look at scales small enough to see them as individuals, rather than as a smooth fluid. In some plasmas, the loosening comes from one source, in others, from something quite different. There is no universal microscopic answer that applies to every case, and one of the most important cautions in this whole field is to resist the temptation to imagine there is. The breakdown of the frozen-in condition is a general requirement, but the specific physics that produces it is a rich and situation-dependent question. What we can say with confidence, standing here at the edge of the current sheet, is what the breakdown must produce, even if we have not yet opened up the mechanisms that produce it. It must produce a small region right in the heart of the thinned current sheet, where the plasma and the magnetic field stop moving in perfect lockstep, where the field is allowed, at last, to move relative to the plasma. That small region is where the ideal description finally, completely gives way, and where an entirely different set of physical effects takes over. It is where the connectivity of the field gets rewritten. It is where the doorway actually opens. Physicists have a name for it, a name that captures exactly what it does. They call it the diffusion region, because it is the place where the field is no longer perfectly frozen, but can instead diffuse, or seep, through the plasma in a way that is strictly forbidden everywhere else. We have not yet stepped inside that diffusion region. We have only walked up to its threshold, tracing how the plasma flows built the current sheet that houses it, and how the ideal description that served us so well finally ran out at its door. But look at how much sharper the paradox has become, and how much closer we are to resolving it. We now understand that the quiet build-up is a large-scale, frozen-in process. Plasma flows stretch, compress, twist, and shear the field, storing energy across an immense volume and driving oppositely directed magnetic regions together. We understand that this pressing together, forbidden by the frozen-in rule from simply blurring the fields, instead squeezes the boundary between them into a thin current sheet, where the field reverses sharply and an intense electric current concentrates. We understand that ideal magnetohydrodynamics correctly predicts all of this right up to the current sheet, and then, precisely there, at that hair-thin, high-gradient seam, breaks down, not because it was wrong, but because the structures have become too sharp and too small for its smooth fluid assumptions to hold. And we understand that whatever physics takes over inside that seam must accomplish one specific, momentous thing. It must let the frozen-in weld fail locally, opening a diffusion region where the field can finally slip relative to the plasma and rewrite its connectivity. That is the stage, fully set. On one side, a vast reservoir of magnetic energy, strained across a structure larger than worlds, pressed together by the ceaseless motion of the plasma. In the middle, a thin current sheet, the boundary where opposing fields meet and where the trusted ideal description gives out. And within it, waiting to be understood, the diffusion region, the small, strange place where the plasma and the field come unstuck, where the lock finally breaks, and where all that quietly hoarded energy is about to find its way out. What remains is to step inside that region and watch, in detail, how the frozen grip actually fails, how the electrons and the ions come loose from the field and from each other, what collisions and resistance and turbulence and pressure each contribute, how the connectivity genuinely changes without any thread ever snapping, and how the reshuffled field, suddenly freed and suddenly straining to straighten, hurls the surrounding plasma outward and converts hours of patient storage into a few violent minutes of heat, light, and racing particles. We are standing at the threshold of the diffusion region, that small, strange place buried in the heart of the thinned current sheet, where the plasma and the magnetic field are finally about to come unstuck. Everywhere else in the vast structure, the frozen-in weld still holds. The field and the plasma still travel as one across a volume larger than worlds. But here, in this tiny seam, something is about to give that gives nowhere else. Let us step inside and watch it happen slowly, because the details are where the real understanding lives, and because the details are exactly what the dramatic phrase, field lines snapping, gets so badly wrong. The first thing to grasp is why the frozen-in condition can fail here specifically, when it holds so faithfully everywhere else. Recall what enforces the weld in the first place. The magnetic field grips the plasma because the field bends any charge that tries to cross a field line, curling its path right back and preventing the crossing. And the plasma grips the field because any attempt to make the field slip relative to the plasma drives powerful electric currents that generate opposing fields, fighting the slippage. This mutual grip depends on the plasma behaving as a smooth, well-organized fluid, where the charges move in orderly, coordinated ways, and the field varies gently across space. But inside the thinned current sheet, none of those comfortable conditions hold anymore. The field reverses across a razor-thin span. The current is jammed into an extraordinarily narrow layer, and most importantly, the layer has become so thin that it approaches the scales at which we can no longer treat the plasma as a smooth fluid at all. The scales at which the individual behaviour of electrons and ions starts to matter more than any averaged, fluid-like description. This is the crucial shift, so let me dwell on it. Everywhere in this story so far, we have been able to talk about the plasma as though it were a continuous substance, a magnetised fluid that flows and stretches and compresses as a coherent whole. That fluid picture works because, on large scales, the countless individual electrons and ions blur together into something smooth, the way a river looks like a single flowing sheet of water, even though it is made of unfathomable numbers of individual molecules. But a current sheet can thin down until its width shrinks toward the natural scales of the particles themselves, down toward the small distances over which an individual electron or ion executes its looping, spiraling motion around the field. And once the structure becomes that thin, the blur no longer holds. You can no longer pretend the electrons and ions are a smooth fluid moving in perfect unison. You have to start paying attention to what they are actually doing as individuals. The fluid description dissolves, and a more detailed, more granular picture takes its place. This granular picture is what physicists call kinetic behavior, the physics of how the particles genuinely move, one population at a time, rather than the physics of a smoothed-over fluid. And here is the beautiful consequence. Electrons and ions are wildly different from each other. An ion is thousands of times more massive than an electron, a lumbering heavyweight compared to a nimble featherweight. Because of that enormous difference in mass, the two respond to the magnetic field on completely different scales. An ion, being heavy, swings in a wide arc around a field line. Its looping motion carries it across a relatively large distance before it comes back around. An electron, being light, whips around the same field line in a much tighter, much smaller loop. This means that as the current sheet thins, there comes a point where the layer has grown thinner than the wide arc of the ions, but is still wider than the tight loop of the electrons. And at that point, something remarkable happens. The ions can no longer stay properly coupled to the field, because the field is now varying over distances smaller than the ion's own natural scale of motion. The ions effectively fall out of the frozen-in embrace first. They stop faithfully following the field lines and begin to plough through more or less on their own inertia, while the electrons, with their much tighter loops, remain coupled to the field down to smaller scales still. So the decoupling does not happen all at once, and it does not happen to everything together. It happens in stages, at different scales, for different particles. First, the ions come loose from the field, in a region of a certain size. Then, deeper inside, in an even smaller and more central region, the field finally varies over scales small enough that even the nimble electrons can no longer keep their grip, and they too come loose. This layered structure, an outer zone where the ions have decoupled but the electrons still follow the field, surrounding an innermost zone where even the electrons let go, is the true anatomy of the diffusion region in many plasmas. The frozen-in condition does not shatter uniformly, it peels apart layer by layer, particle population by particle population, as the relevant scales are crossed, and it is in that innermost zone, where even the electrons have finally slipped free of the field, that the magnetic field is at last able to move relative to the plasma and rewrite its connectivity. Now, I have been describing the decoupling in terms of the particle's natural scales of motion, and that description fits one important kind of plasma especially well, a plasma where the particles are so hot and so sparse that they almost never bump into one another. This is worth naming clearly, because it points to a genuine fork in the physics. In many of the most dramatic settings, the outer atmosphere of a star, the magnetic bubble around a planet, the plasma is so thin and so hot that collisions between particles are extraordinarily rare. A given electron might travel an immense distance before it happens to run into anything. In such a plasma, the frozen-in weld cannot be broken by collisions because there essentially are none. Instead, the weld breaks through exactly the kind of kinetic, individual particle behavior we have been describing. The ions, and then the electrons, decoupling from the field as the current sheet thins to their natural scales, aided by subtle effects in how the particle's pressure and motion are organised inside that thin layer. This is called collisionless behaviour, and the fact that reconnection happens at all in collisionless plasmas, that the field can unstick from the plasma even when the particles never touch, was one of the genuinely surprising discoveries in the history of this subject. But there is another kind of plasma, and in it, the weld breaks by a completely different route. In denser, cooler, more crowded plasmas, the particles collide constantly. Every electron trying to carry current through the sheet is forever bumping into ions, getting knocked off course, scattered, slowed. And this incessant bumping produces something you already know from ordinary wires: electrical resistance. Resistance is nothing more than the friction that charges feel as they try to flow through a material, the accumulated effect of countless collisions impeding their progress. And electrical resistance, it turns out, is precisely a way for the frozen-in condition to fail. When the plasma has resistance, the field is no longer perfectly locked to it. Instead, the field can slowly seep or diffuse through the plasma, leaking across from one region to another the way heat leaks through a poorly insulating wall. In a resistive plasma, the current sheet does not need to thin all the way down to the particle's kinetic scales for the weld to break. The resistance itself, arising from all those collisions, allows the field to diffuse through the plasma and lets the connectivity change. This is called collisional behavior, and it is the mechanism that dominates in the denser, more collisional plasmas found in some laboratory settings and in certain astrophysical environments. I want to be careful here not to turn this into a dry catalogue, because the distinction between collisional and collisionless behavior is not the point in itself. The point is that there is no single universal answer to the question of what breaks the weld. In a hot, sparse, collisionless plasma, it is the kinetic decoupling of ions and electrons at their natural scales, along with subtle effects in the particle's pressure and inertia. In a dense, collisional plasma, it is electrical resistance born of constant particle collisions. And in still other situations, turbulence plays the decisive role, because a current sheet does not have to remain a smooth, orderly layer. It can become unstable and break up into a churning, chaotic froth of swirling plasma and tangled field, and that turbulence can dramatically speed up the breaking of the weld, chopping the smooth sheet into a mess of smaller structures where the field can slip free far faster than it otherwise would. Pressure effects, the way the plasma's own internal pressure is organised across the thin layer, contribute as well. The honest picture is that collisions, electrical resistance, turbulence, pressure effects, and kinetic particle behaviour may all play a role, and which of them dominates depends entirely on the density, the temperature, and the specific conditions of the plasma in question. Reconnection is a general process, a general phenomenon in which the frozen-in weld breaks inside a thin current sheet and the field reorganises. But the detailed microscopic physics that produces the break is genuinely varied. Anyone who tells you there is one clean, universal mechanism behind every case is smoothing over one of the richest and most actively studied questions in the whole field. And this is exactly where we run into what may be the single deepest puzzle in the entire subject, a puzzle that drove the field forward for the better part of a century: the puzzle of speed. It is not enough for the weld to break somehow. It has to break at the right rate, and the right rate turns out to be shockingly fast, far faster than the most obvious physics can explain. Let me lay out the problem, because once you see it, you understand why reconnection has occupied so many brilliant minds for so long. The earliest serious attempts to describe reconnection took the collisional route. Assume the weld breaks because the plasma has some electrical resistance, and calculate how quickly the field can diffuse through it and reorganize. When you do that calculation for the plasma in the atmosphere of a star, you get an answer, and the answer is absurd. Resistance alone, in that hot and sparse a plasma, would let the field reorganize so sluggishly that a solar flare, instead of erupting in minutes, would take weeks, months, even years to release its energy. The simple, obvious mechanism is off not by a little, but by staggering factors, the difference between a minute and a lifetime. And yet flares plainly happen in minutes, so the obvious physics is not just incomplete, it is catastrophically too slow. This gap between how fast reconnection ought to go by the simplest reckoning and how fast it actually goes is one of the most important discrepancies in all of plasma physics, and closing it has been a central quest of the field. The resolution has several threads, and they are genuinely different from anything we have said so far. One thread is that the shape of the current sheet matters enormously. A long, broad current sheet lets the field reorganize only slowly because the plasma has to squeeze out along a great length before fresh field can flow in. But if the sheet is short and open at its throat, the plasma can escape quickly, fresh field can rush in, and the whole process accelerates dramatically. The geometry of the seam, in other words, sets the pace, and finding the geometries that permit genuinely fast reconnection was a major theoretical advance. But the thread that has reshaped the modern understanding is subtler and more surprising, and it connects directly back to the turbulence we mentioned a moment ago. A long, thin current sheet, it turns out, does not like to stay a single smooth layer at all. It is unstable. As it thins, it tends to break up, spontaneously, into a chain of small magnetic islands, self-contained loops of magnetic field, like knots forming along a stretched string, strung out one after another down the length of the seam. These islands are called plasmoids, and their discovery transformed the picture of what a current sheet actually is. Instead of one long, orderly, slowly reconnecting layer, the sheet fragments into a churning chain of plasmoids, with new, thin sheets forming in the gaps between them, and those thin sheets breaking up into still more plasmoids in turn. The seam becomes a hierarchy of structures within structures, a cascade of magnetic islands, and the ever thinner sheets between them. And this fragmentation is the key to speed. Each of those small sheets between the plasmoids is short, and short sheets reconnect fast. The plasmoids themselves get flung out along the seam, carried away by the outflows, clearing space and dragging fresh field in behind them. What was one slow, stubborn layer becomes a swarming, self-renewing chain of many fast little reconnection sites, all working at once. The plasmoids are constantly being born, growing, merging with one another, and being ejected, and in that restless churning the field reorganizes far faster than any single smooth sheet ever could. This is how a real current sheet reconciles the two facts that seemed irreconcilable. Reconnection is slow when you assume a smooth layer, and yet nature reconnects fast. Because nature does not keep the layer smooth, it shreds it into plasmoids, and the shredding is the accelerator. The breakup of the sheet is not a complication that gets in the way of reconnection. It is a central part of how reconnection manages to be quick enough to power a flare in the first place. Notice too how this feeds the runaway character we will come to shortly. A smooth sheet that breaks into plasmoids reconnects faster, and faster reconnection drives stronger outflows, and stronger outflows stretch and thin the remaining sheets, which makes them break into still more plasmoids, each stage feeding the next. The plasmoid cascade is one of the engines of the sudden acceleration that turns a slow trickle into a torrent. Hold that thought, because it is about to matter. Whatever the specific route, and however the sheet fragments to reach its speed, the outcome inside the diffusion region is the same. And now we can finally address the thing we have been circling from the very beginning, what it actually means for the magnetic connectivity to change, and why that is nothing at all like a thread snapping. This is the conceptual heart of the matter, so let us build it up with real care. Return to the picture of the current sheet, with upward pointing field on one side and downward pointing field on the other, and the thin seam between them. Everywhere outside the diffusion region, the frozen-in condition holds, which means that any given parcel of plasma stays tied to its own portion of the field, and the pattern of which regions are magnetically linked to which stays fixed. A field line coming in from the upper left is connected, following the field's direction, to somewhere specific. A field line coming in from the lower left is connected to somewhere else. These connections are rigid, locked in by the frozen-in weld, as unchangeable as the connections in a knot that cannot be untied. But remember what a field line actually is. It is not a physical object, it is a map, a way of tracing the direction of the field through space, and of keeping track of which regions the field links together. When we say the connectivity changes, we are saying something purely about this map, about the pattern of linkage, not about any material thread. And inside the diffusion region, where the field has come unstuck from the plasma, that pattern of linkage is suddenly free to be redrawn. Here is what that redrawing looks like. Imagine following the field along, coming in from the upper left, tracing the direction of the magnetic field as it heads toward the seam. Before the weld broke, that incoming field would have stayed segregated, kept rigidly apart from the oppositely directed field on the other side by the frozen-in rule. But now, inside the diffusion region, where the field can slip through the plasma, the incoming field from the upper left can link up with the field on the far side and continue outward in a wholly new direction, say, out to the lower right, while the field coming in from the lower left links up and heads out to the upper right. The magnetic field has not broken anywhere. At every single point in space, the field still points in some perfectly definite direction. There is no gap, no severed end, no snapped strand. What has changed is the pattern of connection, the way the field routes through the region, the map of what links to what. Regions that were magnetically separate a moment ago are now magnetically joined, and joined in a new configuration that routes the field through the diffusion region and out along entirely different paths. This is why the language of breaking and reconnecting is so misleading, even though the word reconnection is the name we actually use for the whole process. Nothing physical breaks, nothing physical is retied. The field is continuous and smooth everywhere, at every instant. What reconnects is the connectivity, the abstract pattern of linkage that our field line map keeps track of. It is more accurate to say that the field's routing is rewritten, or that its connectivity is reorganized, than to say that anything snaps and rejoins. The thin diffusion region is simply the small place where the field is momentarily free enough from the plasma to be routed differently. And once it is routed differently, the entire large-scale configuration on either side is transformed. Two opposing regions that have been pressed rigidly apart are now magnetically linked across the seam. And that new linkage is a configuration of far lower energy than the strained, oppositely pressed arrangement that came before. And that drop in energy is everything. This is where hours of quiet storage finally cash out in minutes of violence. Remember that the old configuration, two opposing fields jammed together, boundary squeezed to a razor-thin sheet, was a high-energy, strained arrangement, loaded up by all that patient churning of the plasma. The new configuration, with the connectivity reorganized across the seam, is a lower energy arrangement. And whenever a physical system drops from a high-energy configuration to a lower energy one, the difference in energy has to go somewhere. It does not vanish, it is released. This is the moment the reservoir empties. The magnetic energy that had been stored across the vast, strained structure is suddenly converted, right here, into other forms, into the motion of the plasma, into heat, into radiation, and into the wild acceleration of particles. And I want to underline a point that is easy to lose in the drama. Nothing here creates energy. Not one particle of the released energy is made from nothing. Every bit of it was already there, quietly stored in the strained magnetic field, put there over hours by the work the plasma flows did in stretching and compressing and shearing the field. Reconnection does not generate energy. It converts energy that was already stored, unlocking it and turning it loose. The apparent explosion is a conversion, not a creation. Now let us watch how that conversion actually drives the plasma outward, because this is where a property we flagged long ago finally does its work. Recall that a magnetic field behaves as though its lines are under tension along their length, like stretched elastic bands straining to shorten and straighten. In the old strained configuration, the field was bent and stressed. But look at what the reorganized field does the instant the connectivity changes. The newly linked field, routed across the seam, comes out of the diffusion region sharply bent, kinked like a taut band suddenly released at an angle. And a sharply bent field under tension does exactly what a released elastic band does. It snaps toward a straighter, shorter, lower energy shape. This is the metaphorical snap in the phrase we have been unpacking all along, not the snap of anything breaking, but the snap of a bent, tensioned field springing toward straightness, the way a bent bow limb whips forward when the arrow is loosed. And because the field is still frozen into the plasma everywhere just outside the tiny diffusion region, when the reorganized field snaps towards straightness, it grabs the plasma and hurls it along. The plasma is flung outward from the reconnection region in two opposing jets, streaming away along the newly straightened field at tremendous speed. This is the source of the high-speed plasma outflows that are one of the signatures of reconnection. Magnetic tension, released as the reorganized field springs back toward a relaxed shape, converts directly into the bulk motion of the plasma, accelerating great streams of it away from the seam. The stored magnetic energy becomes, first and most visibly, motion. Vast quantities of plasma set racing outward, where a moment before, everything was pressed into stillness. And notice that the plasmoids we met a moment ago are part of this outflow. Those magnetic islands, born in the fragmenting sheet, get swept up and flung out along the jets, so that the outflow is not always a smooth stream, but often a train of magnetic knots hurtling away from the seam, each one carrying off its share of field and plasma. But motion is only one of the forms the released energy takes. As the outflowing plasma streams away, it slams into the surrounding slower plasma and into the reorganized field piled up ahead of it, and all that violent collision converts the energy of motion into heat. The plasma is heated ferociously, driven to temperatures far above what it had before, often reaching tens of millions of degrees, many times hotter than the visible surface below it. And hot, energetic plasma radiates. It pours out light across the spectrum, from radio waves to visible light to the most energetic radiation, carrying off some of the released energy as pure electromagnetic radiation, streaming away at the speed of light. So the reservoir empties into heat and into radiation as well as into motion. And there is one more form, perhaps the most dramatic of all, the acceleration of particles to enormous energies. Inside and around the reconnection region, conditions are exactly right to fling individual charged particles up to speeds approaching the speed of light. The reorganizing field, the intense electric fields that arise within the thin diffusion region, the turbulence, the repeated slamming of plasma against field, and the churning of the plasmoid chain, all of these can seize hold of individual electrons and ions and hurl them to tremendous energies, producing populations of energetic particles that come streaming out of the event far faster than the bulk plasma flows. These accelerated particles are among the most important products of reconnection, and among the most consequential, because when they arrive somewhere, the surface of a star, the atmosphere of a planet, the instruments of a spacecraft, they announce, in the clearest possible terms, that a great reorganization of the magnetic field has just occurred. So the stored magnetic energy fans out into 4 channels at once: the bulk motion of outflowing plasma, the intense heating of that plasma, the radiation it pours out, and the populations of particles accelerated to fantastic speeds. One reservoir, quietly filled over hours, emptying in minutes into motion, heat, light, and racing particles. There is a final feature we have to explain, and it is the very thing that makes reconnection feel like a sudden tearing rather than a gradual leak: the timing. Why does the release begin slowly and then abruptly accelerate into a violent burst? Why hours of build-up and then just minutes of release? The answer lies in the way the process feeds on itself. In the beginning, when the current sheet first starts to thin and the weld first starts to loosen, reconnection proceeds slowly. The field reorganizes at a gentle, unhurried pace. Only a trickle of energy is released, but that trickle changes the situation. As reconnection begins to reorganize the field and fling plasma outward, it clears material away from the seam, and it can drive the current sheet to become thinner still, or to become unstable and break up into the plasmoid cascade we described. And a thinner, plasmoid-riddled current sheet allows the weld to break faster, which speeds up the reconnection, which flings out plasma more forcefully, which thins and destabilizes the sheet even further. Each step makes the next step easier. The process bootstraps itself, accelerating until what began as a slow trickle becomes a torrent, and the bulk of the vast stored reservoir is unleashed in a rush. This runaway, self-accelerating character is why reconnection can lie almost dormant for so long and then erupt so suddenly. The build-up phase is slow because the frozen-in weld is stubborn and the current sheet takes time to thin. The release phase is fast because once the weld begins to break, the breaking accelerates itself. And it is also why reconnection is so difficult to predict precisely in real turbulent plasmas. The moment the process tips from slow to fast depends on a delicate interplay of the current sheet's thinning, the onset of the plasmoid instability, the specific behavior of the particles, the local density and temperature, and the details of the field geometry. A tangle of factors so intricate and so sensitive that pinning down exactly when a given structure will erupt remains one of the genuine challenges of the field. The energy that will be released is stored in plain sight, across a great, strained structure for anyone to see. But precisely when the switch will flip, when the slow build-up will tip into the fast release, hides in the fine details of physics playing out in a seam thinner than worlds are wide. Step back now and take in what we have assembled. We have gone inside the diffusion region, and watch the frozen-in weld fail, not uniformly, but in layers, with the heavy ions decoupling from the field first, and the nimble electrons only at smaller scales still, in the very heart of the seam. We have seen that the weld can break through different physics in different plasmas, through the kinetic decoupling of particles in hot, sparse, collisionless plasmas, through electrical resistance born of constant collisions in dense, crowded ones, through turbulence, through pressure effects, and through the spontaneous fragmentation of the sheet into plasmoids, with no single universal mechanism, but rather a family of processes whose dominance depends on the plasma's own conditions. We have confronted the deep puzzle of speed and seen how the breakup of the current sheet into a churning chain of magnetic islands is a central part of how reconnection reconciles its apparent sluggishness with its actual flare-lighting quickness. We have understood, at last, what it truly means for connectivity to change, not any thread breaking, but the pattern of magnetic linkage being rewritten inside a region where the field has come momentarily unstuck from the plasma, redrawing which regions are joined to which, while the field itself remains smooth and continuous everywhere. We have watched the reorganized field, sharply bent and straining under its own tension, snap towards straightness and fling the frozen-in plasma outward in high-speed jets. And we have followed the released energy as it fans out into motion, heat, radiation, and accelerated particles. Energy that was never created, only converted, drawn from a reservoir filled quietly over hours and emptied in a self-accelerating rush of minutes. What we have not yet done is watch this mechanism at work in the real universe, see it light up the atmosphere of a star, ripple through the magnetic shield of our own planet, and even flare inside the machines we build here on the ground. That is where the abstract mechanism becomes something you can point to in the sky, and something engineers must reckon with in the laboratory. The seam has broken, the energy has poured out. Now we follow it into the places where it actually matters. We have built the whole machine now, piece by piece, from the silent build-up to the explosive release. But a mechanism described in the abstract can feel like a clever story about nowhere in particular. So let us do the thing that turns understanding into conviction. Let us find this process actually at work, in real places, producing real events that people have watched and measured, and in some cases, been endangered by. Because reconnection is not a theoretical curiosity confined to equations, it is happening right now, in the atmosphere of our own star, in the invisible magnetic shell around our planet, and inside machines humans have built on the ground. And once you know what to look for, you start to see the same signature everywhere. Energy stored quietly across a great structure, then released in a sudden reorganization of the field. Begin with the most spectacular arena of all, the atmosphere of our own star. The outer atmosphere of the Sun is a sea of plasma, threaded through with intense magnetic fields, and it is a place of relentless motion. The surface of the star churns and boils as heat rises from the depths, and vast convective flows drag the footpoints of the magnetic field this way and that. Great arches of magnetic field loop up out of the surface and back down again, anchored at both ends in the roiling plasma below. And because the plasma is in constant motion and the field is frozen into it, those footpoints get shuffled around endlessly, dragging the arches with them, twisting neighbouring loops around one another, shearing one region of field against another. This is precisely the quiet build-up we described at the very beginning, now playing out on a colossal scale across the face of a star. Over hours, sometimes days, the magnetic field in an active region of the Sun is wound into more and more strained, more and more energetic configurations, storing an immense reservoir of magnetic energy across a structure that can span distances larger than many planets put together. And then, in some active regions, the strained field is driven into exactly the geometry we studied. Oppositely directed magnetic regions pressed together, a current sheet thinned between them, the frozen-in weld broken in a diffusion region, and the connectivity abruptly reorganized. When that happens, the result is a solar flare. A solar flare is, at its heart, a reconnection event on a stellar scale, a sudden reorganization of the magnetic field in the Sun's atmosphere that releases, in a matter of minutes, an amount of energy that beggars comparison. The reorganized field snaps toward a lower energy shape, flinging plasma outward, heating it to tens of millions of degrees, pouring out radiation across the entire spectrum and accelerating populations of particles to speeds approaching the speed of light. A flare can brighten a patch of the sun so intensely in the most energetic radiation that it briefly outshines the rest of the star at those wavelengths, all of it from a reservoir that was filled silently over the preceding hours by the patient churning of the plasma. Let me try to put a number on that release, because the scale is genuinely difficult to hold in the mind. A single large solar flare can unleash energy on the order of 10 to the 25 joules, a 1 followed by 25 zeros. To make that mean something, consider that all of human civilization, every power plant and engine and furnace on the entire planet, consumes energy at a rate that would take very roughly 100,000 years to add up to what one big flare can pour out in a matter of minutes. And a large flare is often only part of the story. The coronal mass ejection that can accompany it carries its own vast budget of energy in the sheer motion of the plasma it hurls into space. One reorganization of a magnetic field in one region of one ordinary star briefly rivals the output of a civilization across geological time. That is what was quietly stored over those preceding hours in the strained field. And that is what reconnection converts and turns loose. Often accompanying the largest flares is that even more massive expulsion, the coronal mass ejection. Where a flare is chiefly a burst of radiation and heating and particle acceleration, a coronal mass ejection is the wholesale hurling of a gigantic cloud of magnetized plasma off the sun entirely, launched outward into space. Reconnection plays a central role here too. As the strained field reorganizes, it can release a great looped structure of plasma that had been held down by the overlying magnetic field, cutting it loose from the sun and flinging it outward so that billions of tons of plasma go streaming off into the solar system at enormous speed, carrying their tangled magnetic field with them. The flare and the coronal mass ejection are, in many events, two faces of the same underlying reorganization. The field lets go, and both radiation and matter come pouring out. The radiation, travelling at the speed of light, reaches us in a little over 8 minutes. The fastest particles arrive not long after, and the great cloud of plasma, slower but far more massive, can take anywhere from a day to several days to cross the distance to our planet, which means that when a big event erupts on the sun, we often have some warning before the heaviest of it arrives. But here I have to insert a caution, and it is an important one, because it is easy to walk away from a description like that, thinking every flare is the same simple event playing out in the same simple way. It is not. I have been describing the essential mechanism, the common thread that runs through these events, and it would be a mistake to imagine that every solar flare is the result of one perfectly clean, textbook reconnection geometry with two tidy slabs of opposing field meeting along a single neat seam. The real atmosphere of the sun is far messier than that. The magnetic field in an active region can be tangled into fantastically complicated shapes, with many loops and many regions of opposing field, and reconnection can occur in intricate three-dimensional configurations that look nothing like the clean two-sided picture we use to build our understanding. Flares come in a great range of sizes and characters, some modest and some enormous, some accompanied by coronal mass ejection and some not, and the specific way the reconnection unfolds, where the current sheets form, how the field is arranged, how the released energy is partitioned among heat and radiation and particle acceleration, varies from event to event. The clean geometry we studied is the right way to understand the mechanism. It is not a claim that every real flare is that simple. The underlying principle is universal. The specific realization is endlessly varied, and part of what makes solar physics so alive as a field is precisely the effort to understand that variety. Now follow the released energy outward from the sun, because it does not stay put. The particles accelerated in a flare go streaming across space. The great cloud of a coronal mass ejection barrels outward through the solar system, and some of it, sooner or later, arrives at our own planet. Which brings us to the second great arena where reconnection shapes events we can actually observe: the magnetic shell around the Earth. Our planet generates its own magnetic field, produced deep in its molten metal interior, and that field extends far out into space, forming a vast magnetic bubble that surrounds the Earth. This bubble is called the magnetosphere, and it is our planet's shield, deflecting the relentless stream of magnetized plasma that blows off the sun, the solar wind, and preventing most of it from reaching us directly. The magnetosphere is not a passive, inert shell, though. It is a dynamic, plasma-filled, magnetized structure, and it is a place where reconnection happens continually, shaping the way our planet interacts with the sun. Consider what happens on the side of the magnetosphere that faces the sun. The solar wind comes streaming in, carrying its own magnetic field frozen into it. When that incoming field is oriented oppositely to the Earth's field, at the boundary of the magnetosphere, you have exactly the setup we have studied all along. Two regions of oppositely directed magnetic field pressed together by the flow of the plasma. And so, on the sunward side of the magnetosphere, reconnection occurs. The solar wind's field and the Earth's field reorganize their connectivity across a current sheet at the boundary, and in doing so, they link together. The field of the solar wind becomes connected to the field of the Earth. This is called dayside reconnection, and it is the doorway through which the solar wind's energy and plasma get transferred into our magnetosphere. Without it, the shield would be nearly perfect and almost sealed. Because of it, the magnetosphere is coupled to the sun, and a steady stream of energy is fed into it. Once that coupling opens on the dayside, the linked field lines get dragged by the flowing solar wind back over the poles and stretched out behind the planet, on the side facing away from the sun, into an enormous, elongated structure called the magnetotail. This is the quiet build-up again, wearing a new costume. The solar wind drags the field back and stretches it, storing energy in the strained, stretched configuration of the magnetotail, winding the tail tighter and tighter, exactly as convective motions load the field in the atmosphere of the sun. Energy accumulates in the stretched tail, quietly, as the coupling continues to feed it, and then, in the stretched magnetotail, the strained field reorganizes. Oppositely directed regions of field in the tail get pressed together, a current sheet thins between them, the weld breaks, and the connectivity abruptly changes. Reconnection, once again, doing exactly what it does. The stretched tail snaps back toward a relaxed configuration, flinging plasma both outward, away from the Earth, and inward, back toward the planet. The inward hurled plasma, energized by the reconnection, comes streaming down along the field lines toward the Earth's polar regions, and when it slams into the upper atmosphere, it excites the atoms and molecules of the air, which then glow. That glow is the aurora, the shimmering curtains of light that dance over the polar skies. The northern and southern lights are, in a very direct sense, a visible consequence of magnetic reconnection in the magnetotail. Stored magnetic energy, released in a reorganization of the field, delivered down to the atmosphere as streams of energetic particles that make the sky itself luminesce. This whole cycle, energy coupled in on the dayside, stored in the stretched tail, then released in a burst of tail reconnection that lights the auroras and stirs up the whole magnetosphere, is called a substorm, and it plays out over and over, sometimes several times a day. And when a large coronal mass ejection from the sun slams into the magnetosphere, the whole process is driven far harder, producing a geomagnetic storm, intense reconnection, brilliant and widespread auroras seen far from the usual polar regions, and significant disturbances to the magnetosphere. These storms are not merely beautiful, and here it is worth pausing on two real events, because they turn the abstraction into something with genuine stakes. In late August and early September of 1859, the sun launched one of the most powerful coronal mass ejections in recorded history straight at the Earth, in what is now called the Carrington Event, after the astronomer who watched the flare that preceded it. When the cloud struck the magnetosphere, the reconnection it drove was so intense that auroras were seen not only over the poles, but far down toward the equator, in places that essentially never see them. The night sky glowed so brightly in some regions that people reported being able to read by it, and the shifting fields induced currents in the telegraph lines that were, at the time, humanity's most advanced technology. Telegraph systems failed, sparks jumped from equipment, and in some cases, operators found they could send messages with their batteries disconnected, the lines driven by the storm itself. That was in a world with almost no electrical infrastructure to damage. Now bring that forward. In March of 1989, a far more modest storm than the Carrington Event struck a world utterly dependent on electricity. The geomagnetic disturbance induced currents in the power grid, serving the Canadian province of Québec, and within a matter of seconds, those currents overwhelmed the system and collapsed it, plunging millions of people into darkness in the middle of winter for around 9 hours. A reorganization of magnetic fields in the tail of our planet's magnetosphere, the same fundamental process that paints the auroras, had reached down through many hundreds of thousands of kilometers of space and switched off the power for an entire region. This is why reconnection in the magnetosphere is not an abstraction. The same energetic particles and shifting fields that light the polar skies can disrupt satellites, corrupt communication and navigation signals, and induce grid-wrecking currents on the ground. And space weather forecasters watch the sun closely for exactly this reason. A repeat of a Carrington-scale event today, in a civilization laced with power grids and satellites, is one of the natural hazards that genuinely worries the people who study these things, because the reorganization of the field around our planet has consequences that reach all the way down to the surface, and all the way into the machinery our lives depend on. There is something else worth pausing on in this magnetospheric story, because it deepens the picture of the mechanism itself. Notice that the plasma of the magnetosphere and the solar wind is extraordinarily thin and hot, so sparse that collisions between particles are exceedingly rare. This is a collisionless plasma, the very kind in which the frozen-in weld cannot be broken by ordinary electrical resistance, because there are hardly any collisions to produce resistance. And yet, reconnection unmistakably occurs there. The auroras prove it, the substorms prove it. This is why the study of the magnetosphere has been so scientifically valuable. It is a natural laboratory for collisionless reconnection, sitting right on our doorstep, close enough that spacecraft can fly directly through the reconnection regions and measure what the particles are doing as the weld breaks. Missions have flown squadrons of spacecraft in tight formation straight through the diffusion regions of the magnetosphere, catching the ions and electrons in the very act of decoupling from the field at their different scales, precisely the layered breaking of the weld we described. So the abstract picture of ions coming loose first, and electrons only at smaller scales still, is not merely theory. It has been measured directly in the reconnection regions around our own planet. The magnetosphere lets us reach out and touch the mechanism. Now let us leave the sun and the earth behind and answer a question that the whole journey has been implicitly raising. Is reconnection just a thing that stars and planets do, a quirk of solar and terrestrial physics? Or is it something more general, a fundamental behaviour of magnetized plasma wherever it is found? To answer that, we turn to a setting utterly different from the atmosphere of a star or the shell around a planet. A machine built by human hands, here on the ground, in the effort to harness the power source of the stars themselves. For decades, physicists and engineers have been pursuing controlled nuclear fusion, the attempt to fuse light atomic nuclei together and release energy, the same basic process that powers the sun, but tamed and contained in a device on Earth. To do that, the fuel must be heated to temperatures far hotter than the core of a star, hot enough that it becomes a plasma. And that blazing plasma must somehow be held in place without touching the walls of any container, because no material could survive contact with it. The solution, in the most prominent designs, is to hold the plasma with magnetic fields, to build a magnetic bottle, a carefully shaped configuration of intense magnetic field that confines the hot plasma and keeps it suspended away from the walls, trapped by the very frozen-in behaviour we have studied throughout. The charged particles of the plasma, bound to follow the field, are corralled into the shape the magnets dictate. In the most developed of these designs, a donut-shaped chamber holds the plasma in a ring, wrapped in a helical magnetic field that winds around and around to keep the plasma from drifting into the walls. But here is the difficulty, and it is a difficulty that connects directly to everything we have built. That confined fusion plasma is a hot, magnetized, current-carrying plasma, exactly the kind of substance in which reconnection can occur. And in these fusion machines, reconnection does occur, and it can be a genuine problem. As the plasma is heated and confined and driven with electric currents, the magnetic configuration inside the machine can develop exactly the conditions we have described. Regions where the field is strained, current sheets where opposing fields are pressed together, and diffusion regions where the frozen-in weld breaks and the field reorganizes. When that happens inside a fusion device, the reconnection can suddenly rearrange the magnetic structure that was doing the confining, dumping energy in a burst, disrupting the careful containment, and in some cases, causing the plasma to lose its confinement altogether. One of the clearest examples has its own vivid name, the sawtooth crash. In the hot core of a magnetically confined plasma, the temperature and current can build up steadily, climbing higher and higher until the magnetic configuration in the center reaches a tipping point. At that moment, reconnection abruptly reorganizes the field in the core, and the built-up heat and pressure in the center are suddenly flung outward, dropping the core temperature in a flash before it begins climbing again, only to crash once more when the tipping point returns. Plot the core temperature over time, and you get a rising ramp, a sudden drop, another rising ramp, another sudden drop, a pattern like the teeth of a saw, over and over. Each of those crashes is a reconnection event, the same slow build-up then sudden release rhythm we have followed all along, playing out not in the atmosphere of a star, but inside a machine on a laboratory floor, on a timescale of a fraction of a second. The same fundamental process that lights a solar flare or paints an aurora, here, ticks away as a built-in heartbeat of the fusion plasma. Sometimes merely a nuisance that limits how hot the core can get, sometimes a trigger for larger, more damaging disruptions. This is a striking demonstration of how general reconnection really is. Here is a plasma created by humans, in a machine, for a purpose that has nothing to do with stars or planets, and yet the same physics asserts itself unbidden. Strain the field, form a current sheet, break the weld, and the field reorganizes and dumps its stored energy. Whether the plasma is in the atmosphere of a star, in the magnetotail of a planet, or in a magnetic bottle on the ground. But there is also a flip side, and it points to something hopeful. Because these devices are machines, in a laboratory, with instruments packed all around them, they let physicists study reconnection under controlled conditions, in a way that is impossible for a distant star. In fact, researchers have built experiments whose entire purpose is to create reconnection deliberately and watch it happen. Chambers in which two loops of plasma, each carrying its own magnetic field, are driven together on command so that a current sheet forms between them and the weld breaks right in front of a dense array of probes. In these dedicated reconnection experiments, physicists can place their instruments exactly where the diffusion region will form, trigger the event when they choose, and measure the field and the particles as the connectivity changes, testing, directly and repeatedly, the very ideas about kinetic decoupling and current sheet fragmentation that we spent so long building up. The fusion machine and the reconnection experiment are thus two faces of the same coin. Places where reconnection is a nuisance to be managed, and places where reconnection can be summoned, dissected, and understood. And the reach of the process does not stop even there. Wherever magnetized plasma is strained and driven in the universe, reconnection appears. In the extraordinary environments around some of the most extreme objects in the cosmos, around neutron stars and black holes, where plasma swirls in and magnetic fields are wound to titanic intensities, reconnection is thought to play a central role, powering the release of prodigious amounts of energy and helping to accelerate particles to almost inconceivable speeds. Great jets of plasma seen streaming out of the centers of some galaxies, shot out across distances that dwarf the galaxies themselves, are believed to involve magnetic reconnection in their launching and in the acceleration of the particles that make them shine. In the disks of plasma spiraling in toward compact objects, reconnection helps convert magnetic energy into heat and radiation. From the modest substorms in the tail of our own magnetosphere to the most violent particle accelerators in the universe, the same essential mechanism recurs. Strained field, thin current sheet, broken weld, reorganized connectivity, released energy. It is one of the truly universal processes in the physics of the cosmos, a general behavior of magnetized plasma that shows up at every scale, from a machine on a laboratory bench to the environs of a black hole. That universality is worth sitting with for a moment, because it is easy to lose in the parade of examples. What makes reconnection so important is not any single place it happens, but the fact that it happens everywhere magnetized plasma is found. And magnetized plasma is, by far, the most common state of ordinary matter in the visible universe. The stars are plasma. The space between the stars is plasma. The material swirling around black holes is plasma. Nearly everywhere you look, the visible universe is made of the charged, magnetized substance in which reconnection operates. And so this one mechanism, the breaking of the frozen-in weld inside a thin current sheet and the reorganization of the field that follows, is one of the great universal engines of energy release in the cosmos, quietly and violently converting stored magnetic energy into heat, light, motion, and racing particles across an unimaginable range of settings. Now at last, let us return to where we began, to the question in the title that has been waiting patiently through this entire journey. Why do magnetic fields suddenly tear open inside plasma? We can finally answer it, and answer it truly, without any of the misconceptions that make the question so tempting to get wrong. The first thing to say, plainly and firmly, is that magnetic fields do not tear like material objects. Nothing rips, nothing snaps. A magnetic field is not a fabric or a rope or a bundle of threads that can be torn apart. It is a smooth, continuous physical condition of space, and throughout every event we have described, every flare, every substorm, every sawtooth crash in a fusion machine, the field remains smooth and continuous at every point. There is never a gap, never a severed end, never a broken strand. The dramatic image of field lines fraying and snapping, which is how this process is so often carelessly described, is simply wrong. Field lines are a map of the field's direction and connectivity, a bookkeeping device, not a material thing, and a map cannot tear. So what does tear open? What is the sudden rupture that the title points to, if not the field itself? The answer is that what tears open is the previous arrangement of the field, the old configuration, the stored, strained, high-energy pattern that the plasma had spent hours quietly building. The tearing is the collapse of an arrangement, not the breaking of an object. For hours, the churning motion of the plasma winds the frozen-in field into an ever more strained configuration, pressing oppositely directed regions together, storing energy across a great structure. That strained arrangement is metastable, held in place by the stubborn, frozen-in weld, drawn tight like a bow that no one has yet loosed. And then, in one small place, in the thin current sheet where the weld can no longer hold, the frozen grip fails inside a diffusion region. In that tiny region, and only there, the field comes unstuck from the plasma, just enough to reorganize its connectivity. And the instant the connectivity can change, the whole strained arrangement is free to collapse into a lower energy configuration, releasing all the energy that had been stored across the vast structure. That collapse, that sudden reorganization of a configuration built up over hours, triggered by a localized breakdown in a seam vanishingly small compared to the structure it releases, is the tearing open. It is real, it is sudden, and it is violent. But it is the rupture of an arrangement, not of any physical thing, and this resolves the paradox that opened our journey. We began with the mystery of how energy could build quietly for hours and then release in minutes, as though the field had torn itself apart. Now we can see precisely how. The build-up is slow because it is a large-scale, frozen-in process, the patient loading of a great structure by the ceaseless motion of the plasma. The release is fast because it is triggered in a tiny place, a thin current sheet where the frozen-in weld breaks, and because, once the breaking begins, it feeds on itself and accelerates, tipping from a slow trickle into a runaway torrent that empties the reservoir in a rush. The vast scale of the storage and the tiny scale of the trigger are not a contradiction. They are the two halves of the answer. Energy gathered slowly across a region larger than worlds finds its exit through a doorway thinner than worlds are wide, and everything that pours through that doorway does so all at once. So when you see a solar flare brighten a patch of the sun, or watch the auroras ripple over the poles, or read about a sawtooth crash limiting the confinement in a fusion machine, or hear of titanic jets shooting from the hearts of distant galaxies, you are seeing the same thing each time. You are seeing a magnetic field that was quietly wound into a strained, energetic arrangement by the motion of a plasma. And then, in a small region where the frozen bond between plasma and field broke down, allowed to reorganize itself into a relaxed, lower energy shape, snapping towards straightness, flinging plasma outward, and pouring its long-stored energy into heat, into radiation, into motion, and into particles racing at nearly the speed of light. No thread ever snapped, no fabric ever tore. What tore open was an arrangement of fields and currents and charged particles, held together by the physics of plasma, released by that same physics the moment conditions in one small seam let the field reorganize. The sudden, violent rupture is nothing more and nothing less than a rapid reorganization, and understanding it means understanding one of the great universal engines by which the magnetized universe turns quiet, stored energy into sudden, spectacular light.